Well, here we've got a silver and cadmium cell. It's expensive once you're dealing with silver. You've got to pay for it, even if it's the silver ions. And these silver ions are grabbing electrons from the cadmium to make some pretty silver crystals here. So you're not going to lose any money. I mean, you're going to start with silver ions. You've got some silver metal. You guess you could sell it later. And here's the balanced reaction where you end up having twice as many silvers for every one cadmium, because the cadmium is going to give up 2 electrons and each silver is going to only need 1. So they run this thing. This thing has got a positive voltage, 1.2 volts, so it's going to have a K of like 10 to the 30. It's going to keep on going and going until all this cadmium metal is gone and all this silver ion is changed into silver. And it's run for a while. They use it instead of having a light bulb here. They've got a motor that runs for 5 hours, so half a day. And they find out that the concentration of the cadmium nitrate increases. And that's because the cadmium is being used up. This cadmium bar is being turned into cadmium ions. So in our product here, we started off standard, 1 molar. I mean, that's our standard situation where both things are 1 molar. Remember, we always start with the same molarity when we're dealing with standard voltages. So what must have happened is, let me get my text here and toss in, we must have increased plus 0.20, and I'll put down moles, keep the units in terms of getting cadmium ions. If you multiply this 0.2 times 6.02 times 10 to the 23, you'll have that many cadmium ions being made as this cadmium metal disintegrates. So you could figure out really how many grams of cadmium would disappear, 0.2 of a mole. And we'd look up the molar mass, multiply it. But of course, this is our change row, and we know the change row, we make our products. Therefore, the change here is going to be stoichiometric, 2 and 1. So our silver, let me just copy this again and paste it, is not going to be plus, it's going to be used up. Our silver ions are going to disappear, changing into silver metal. So our silver metal decreases, and we have 2 every 1, so I'm going to change this to twice as much, 0.4 of a mole. Silver is about 180 grams per mole, about half of that, and we could find out how many grams of silver we'd have grown on here. That's quite a few grams. This is a pretty good size cell, but of course it's been running for 5 hours. So we multiply 0.4 times the atomic mass of silver, and we find out how many grams of silver are being collected here that we could later sell. So the silver ion is lost, and we, at the end of 5 hours, will have, I'll do that subtraction, I won't need that moles. We're just going to have 0.6 of a mole of silver ions left. So we could run this for a while longer because we've got quite a bit of silver ions left, and we could make quite a bit more silver. So this is a pretty standard stoichiometry. I'm not going to say simple because, good grief, stoichiometry, just the word itself, it doesn't, defies simplicity. So if you understand this, you remember our unit 3, where we talked about stoichiometry, where if you know a change, you can use the change row to find out everything that happens as long as you're dealing with moles. Okay, so now at the end of 5 hours, we will have had that mass change. And I could have asked for that, and on FRQ probably they would have. But we want to know how many electrons. Well, here we know that we had a change of 0.4 of a mole of electrons. And the silver has 1 electron per atom. It's not like cadmium where we have 2, so we can just take that 0.4 of a mole and put it right here. 0.40 moles of electrons. For a chemist that makes sense, but coulombs is used so often in terms of amps and watts and current. And so we've got to deal with the physics in those units, and we're going to have to change moles of electrons into coulombs, which is another measure in terms of like dozens. And your chart here, this is from the equation sheet, says that there are 96,485 coulombs. So if you're counting electrons using coulombs instead of moles, we would take the moles and multiply it times 96,485. And let me get my calculator up. Nope, no, it's not my calculator. Where's my calculator? Let me get this back, and I'll get back to my problem and bring my calculator up, which I'm looking for right now. Here it is. And let me just clear it because it's not quite cleared yet. Clear. And we'll do that problem. That's going to be 4/10, 0.4 moles. That's what a chemist understands. Physicists like to use coulombs. So times 96,485 times 96,485, what we call coulombs. If we wanted electrons, we multiply by the Avogadro number. And let me double check if I remember that number correctly. 96,485, indeed. And this will be the two significant digits. Calculator, and that would be my answer, 38,600. I should probably round it to 39,000, but because we're dealing with WebAssign likes 3 sig figs, we'll put that number down. 38,600 coulombs. 38,600, 3 significant digits, even though I only should have 2. Coulombs of electrons. And that answers our question. But let's go one step further, because I could have asked one more question. What was the current, assuming that our movement of electrons was constant? And there's an equation here. This is current, which comes in amps. You take your coulombs and divide it by time. In fact, that's one of the reasons we've got coulombs, so you can figure out amps, which is something that a lot of people understand in terms of electricity. So I'm going to take that, and it was 5 hours, so I'm going to divide that by the time. The time's got to be in seconds. That's our unit. And I'm going to go to parentheses, and let's see, 5 hours times 60 minutes in an hour times 60 seconds in a minute. Close our parentheses and find out how many amps this motor was running. About 2 amps. Okay, that's a pretty heavy motor. I mean, this would be probably running a furnace. A typical car will run, if the EV will run about 20 to 30 amps. So if we had 20 to 30 of these silver cadmium batteries, we might be able to get a car to run for a while. And of course, the interesting thing is that electrical vehicles are running with batteries, where you've got one substance, right now lithium, who knows what it'll be in the next few years, sodium, which will be gaining electrons or losing electrons, and where there'll be a salt bridge, and where you will have a moles of electrons moving through electric wires that will move your car, and there'll be a salt bridge in that battery underneath your seat. And that's the real trick to making a good electric vehicle battery, is to have a salt bridge that can handle those huge changes in current. All right, there's batteries, and I tossed in a few amps as a special added treat. Quick treat, I thought I'd show you some crystals, silver ions changing into silver metal like they would at the cathode in that galvanic cell. There it is, beautiful silver crystals.